Hello, this is Project Group 2. My name is Linnea.
And my name is Daniel.
This is our presentation for the project in the signal processing course. Introduction. Sound is a mechanical wave motion that is created by vibrations in a medium, most commonly air. These vibrations generate pressure variations in the air, and these vibrations travel as waves from the audio source. When the audio source vibrates, altering regions of compression and refraction are created in the air, and it is the pressure changes caused by these alterations that we perceive as sound. Sound waves can have different waveforms, including sine waves, square waves, and triangular waves. These shapes influence the characteristics of sound. The frequency of sound waves is measured in hertz, and is a measurement of how many peaks of the sound wave occurs each second. Higher amplitude corresponds to louder sound. Loudness is subjective and relates to the intensity of pressure variations. Higher frequency yields higher pitches and vice versa. The human hearing range varies with age, but the typical audible range is around 20 to 20,000 Hz. A bass voice sings at around 80 Hz, while a soprano can sing at 260 Hz, meaning that it would be within this range that most human sounds can be expected. Consonant sounds, which often include higher frequency components, can extend into the higher pitched components. Sounds like S, sh, and z have higher frequency components. It is important to note that individual variations exist and the specific frequency characteristic of speech can vary between speakers and cultural context. In music, pitch is related to musical intervals and scale. Instruments like pianos or guitar exemplify this, where each key or string represents different frequencies and consequently pitches. Resonance is a crucial aspect of sound production. In musical instruments, resonance occurs when the natural frequency of the instrument matches the frequency of the vibrating source, enhancing the sound. The body of the violin acts as a resonator, amplifying the sound produced by the vibrating strings. The resonance is influenced by the shape, size, and materials of the violin. The materials used in musical instruments, as well as the technique employed by a musician, impact the acoustic properties. Our signal is a recording of a violin playing an A note with a TV on in the background. So it's an audio signal. The signal was acquired using an app for sound recording on a mobile phone. The sampling rate is 48,000 Hz, recorded over a 10-second period. The smartphone doesn't add any filters, however, it uses variable bitrate, which is a compression technique used to dynamically adjust the bitrate based on the complexity of the content, so it does not directly involve signal filtering. Our signal was originally recorded on an iPhone 12 and saved as an MP3 file. MP3 uses lousy compression, discarding some audio data to reduce file size. It achieves higher compression ratios while maintaining audio quality. MP3 supports variable bitrate encoding, allowing higher bit rates for complex audio passages and lower bit rates for simpler sections. While MP3 achieves significant compression, it involves a trade-off with some loss of audio information, particularly at lower byte rates. Higher byte rates, however, offer better audio fidelity. MP3 is universally supported across various devices and platforms, making it one of the most compatible audio formats, which is relevant in our project since we need to export the files across devices and into MATLAB so that we can filter it. We later discovered that it is possible to change the settings on the phone so that the file was saved as an M4A file. And because it is recorded on an iPhone, it supports Apple Lossless Audio Codec, which is a type of lossless compression like MP3. M4A supports variable bitrate encoding. It is known for preserving more audio detail at lower byte rates compared to MP3. M4A is well supported within the Apple ecosystem, but may require additional software or conversion for broader compatibility outside Apple devices, which we thought might not be ideal for our project, but turned out this lossless compression option preserved more audio detail while still being compatible with MATLAB, aligning with our goal of accurate signal filtration.
As said before, our signal is a recording of a violin playing an A note on in the background. The sampling rate is 48 kilohertz and recorded over a period. And now we expected the signal to be composed of harmonic frequencies of A note, which up there is any frequency that is around 27.5 hertz times 2 to the power of n integer from 0 to I. So for example, 440 hertz and 880 hertz part of the A note. And we also expected to get noise from frequency. And in the frequency domain, prominent peaks are evident corresponding to the violin. Notably, there's a distinct larger peak at 1300, which during the course project became identified as the. Its origin was initially unknown and posed a question for investigation. Smaller peaks observed can be attributed to background noise. Examining the time domain reveals still on the
Oh, sorry.
examining the time domain reveals amplitude inconsistency, consequence of the note being played by a human. The variations in pressure on the bow against the strings, coupled with the nuanced movement required, subtle patterns in the signal. For instance, a discernible pattern emerges wherein the amplitude gradually ascends, followed by a decline, subsequently another ascent. The ascending amplitude corresponds to the player naturally increasing pressure with the bow, influenced by gravitational force and growing confidence in producing the correct tone. Conversely, the rapid ascent in amplitude occurs when the bow changes direction, necessitating a momentary pause in play before resuming. The inconsistent signal at the beginning and the end is simply the playing starting and ending. Now is the next slide. For our project plan, we had following research. Well, originally we had what filters are needed to efficiently remove noise surrounding violin playing. Could we reverse it and remove the violin? They were, though, slightly altered after starting the project, and they ended up being if we can talking and have only the violin left. Firstly, if we can reverse it and have only talking left, and also what was this at around 1300? In order to find this, we constructed a digital bandpass filter, extract that specific, and then listen to it. And then it was clearly a sound component of the violin, but it was not part of the frequency belonging to the A note, but rather an E note. Then, once we had found that, we continued our filtering, but filtered out specifically the A notes, and that was done in much the same way. A number of bandpass filters were constructed at all the resonant belonging to the note in question, from 27.5 Hz up to 7040 Hz. This way, the note produced by the violin was isolated and could either be played by itself or be subtracted from the original recording, yet only the TV sound. In all cases, we found that grade 6 Butterworth bandpass filter made with MATLAB's own filter designer worked well. Then at results, in examining the process signals within both the time. Oh, sorry, right, this is.
When examining the processed signals within both the time and frequency domain, notable characteristics emerge from the filtration of the recorded audio. The processed signals in the time domain reveal distinct patterns. In the case of isolating the violin's tone, the resulting waveform is much smoother once the noise from the TV was removed. The attempt to filter the TV sound was now far less affected by the turns of the bow, indicating a partial isolation. Transitioning to the frequency domain, the Fourier transform highlighted the frequency components present in the signal. For the filtered violin tone, the dominant peak aligned with the expected frequency of the A note. In contrast, the filtration of TV sound exhibited a substantial reduction in frequencies associated with the violin, yet residual peaks hinted at the challenge of complete isolation. Were the results as expected? The results generally aligned with expectations given the complexities of isolating specific sound resources in a mixed signal. The ability to preserve the primary frequencies of the A note in the violin tone filtration was anticipated, although some residual frequencies were inevitable. The challenge in fully isolating the TV sound while reducing the impact of the violin was expected due to the overlapping frequency components. So removing the TV sound and keeping only violin. The method was relatively successful, preserving the essence of the violin's tone. The imperfections observed were consistent with the inherent challenges of filtering complex audio signals and isolating TV sound. While not perfect, the reduction in the impact of the violin demonstrated partial success. The presence of residual frequencies highlighted the intrinsicies of isolating overlapping sound sources. And lastly, identifying the mystery frequency. The unexpected frequency was successfully identified as a resonant frequency of the E note. This discovery provides valuable insight into the nuances of the violin's performance. And now we're gonna play all of our signals. So we will start by playing our original signal.
And then signal without the violin. Then only the violin without the T. Finally, the mystery signal. And so, conclusion. This project we explored signal processing, particularly in the realm of audio signals and filtering. By recording the sound of a violin while background noise active, we formulated these 3 research questions to investigate 5 various filtered the violin's tone, the A note, and the results demonstrated a relative successful filtration in isolating the violin, although some associated. It is crucial to note that despite minor shortcomings, the technique managed to create a clear audio representation of the violin's tone. When it comes to filtering the TV sound, though, well, isolating only the TV proved to be a challenge, with some frequencies from the violin still audible, speculated to be the result of both the 1323 mystery and others like it. Nevertheless, the impact of the violin was reduced. This outcome indicates both successes and challenges in isolating specific sounds in signal. sound sources. Identification of the mystery. 1300 hertz was that, well, while working with the signal and unexpected frequency discovered, and it was then later identified as a resonance E note violin rather than the A note. This phenomenon can be attributed to human factors such as tuning errors or slight imprecision during playback. It could also be noted that the A and E strings are right next to each other on the violin, so that it would vibrate from its proximity to the string while being played, or simply that it was partially played by the bow while playing the A note on accident. Results fine with questions, but it is essential to acknowledge certain limitations and complexity process. Depending on the objective of the filtration, different methods and adjustments enhance the quality of the results. When it comes to reliability and actions, well, to increase reliability results, future work could involve fine-tuning algorithms and utilizing advanced techniques to reduce overlapping frequencies, as well as finding and filtering more stray notes from the violin. Additionally, a more precise calibration of the violin and recording equipment could enhance the accuracy. Reflection and conclusion. The work has contributed to an increased understanding of signal processing and integration of audio signals. Despite some challenges, the results indicate the possibility of selectively isolating sound sources. Knowledge of the unexpected resonance frequency also highlights the importance of considering human factors in signal analysis. In a retrospective view, there is always the opportunity to improve and refine methods based on obtained results. Thank you very much for listening to our presentation.